Hello and very good afternoon, everyone. I'm Mohammad Tehrani and would like to welcome you all in the fourth session of the first edition of the Water Whispers Wednesdays webinars. This is a sharing time which is planned to be held a couple of times during the year, sharing the hydraulics and water relevant issues. For those sessions where the speakers will attend in person, the webinar will be conducted in hybrid mode, and unfortunately, this is not the case this time as well. Each session will feature dynamic presentation lasting approximately 30 to 40 minutes, followed by the interactive 20 minutes of question and answer session. Before we dive into the talk, a quick reminder to stay engaged. Please feel free to ask questions using the chat box, and we will address them in the dedicated Q&A session at the end, or you could turn on your microphone and camera and ask it directly. Today is no exception, and we have a distinguished speaker who will share his expertise on the estimating flow dynamics and sediment transport using entropy theory. Whether you are a pioneer, senior, professional, or just a young beginner in this area, get ready for an engaging and informative session. Without further ado, let me introduce our speaker for today. Farhad Bahmanpuri received his master's degree in civil engineering, hydraulic engineering from the University of Tehran in 2013. He began his PhD in civil systems engineering at the University of Naples, Federico II in Italy. From May 2017 to August 2017, he attended the University of Queensland to conduct his experimental research at the Hydraulic Laboratory of University of Queensland. And finally, he accomplished his PhD dissertation entitled Experimental Study of Air Entrainment in Hydraulic Jumps on Rough Bed, under the supervision of Professor Carl Gualtieri and Hubert Chanson in 2019. In September 2020, he joined the Research Institute of Geohydrological Protection of the National Research Council in Proja as a postdoc fellow working on some huge national and European projects. His research work includes application for the entropy theory to estimate cross-sectional velocity distribution, river discharge, and sediment transport relying on the surface velocity collected by the remote sensing techniques. Farhad, thank you so much for accepting our invitation and for being with us today. The floor is yours.
Hello and good afternoon, everyone, or good morning, wherever you are in the world. First of all, thank you, Mohammad, for your invitation. I'm honored by your invitation to have this talk for researchers about our recent research or ongoing research projects on the applications of the entropy. So today I will present some of the new findings on the application of this model. Let me share my screen. Can you just tell me that you can see the screen?
Yes, we have received your screen very well. You could go ahead. Thank you.
Okay, thank you. The topic that I'm going to present for you today is the estimation of flow dynamics and sediment transport using the entropy approach, which is the theoretical method. As you know, floods can result in loss of life, damage to infrastructures, economical setbacks, and negative impacts on environmental and agriculture. Just 2 weeks ago, we faced Hurricane Helen in the United States that resulted in at least loss of 30 people. So, as you know, different methods commonly are used to study the floods, such as hydrological and hydraulic modeling, remote sensing techniques, field surveys, and investigation of the gauge stations data. Among the characteristics of the floods, river discharge play a crucial role in various aspects such as water supply planning, reservoir management and operation, hydropower generation, and especially predicting and controlling floods, and also other hydrological applications. So, as probably you know, traditional techniques to measure flow characteristics are usually costly, time-consuming, and dangerous for operators, especially for high flow conditions such as flood condition. No one can go to do in situ measurements. Also, they are not feasible for remote and inaccessible locations. So, to overcome this challenge, using the remote sensing data and theoretical methods are of particular benefits. In this direction, in 1989, Q developed a theory, entropy theory, that can estimate the distribution of velocity in rivers, relying on only surface velocity. After that, since 2004, Marmarco et al., they developed and simplified and extended the model for different flow conditions based on different surface velocity measurements. So the concept of model is that using the my apology. So the concept of model is using the surface velocity to first finding the anthropic parameter, to calibrating the anthropic parameter based on the average cross-sectional velocity and maximum velocity in each cross-section. Then using the surface velocity to find the maximum velocity. As you know, when we have a second recurrence in rivers, the maximum velocity usually occurs below the surface velocity. The phenomenon is the velocity dip. So we have the maximum velocity below the surface, water surface. So using the surface data first, we find the maximum velocity below the surface. Next, we applied some methods to calculate the location of the maximum velocity below surface, or we can say the location of the velocity dip. Next, we use this data as an input for entropy model. So overall, we use the surface velocity and bathymetry for each cross-section to find the distribution of the velocity at each cross-section. Let me now explain you some applications of the model. First, for a large-scale rivers, we use the data of the Amazon River. As you know, Amazon River, in terms of discharge, is the largest river on the earth, with the discharge, average discharge of the 200,000 cubic meter per second. So we specifically studied the confluence of Rio Negro and Rio Solimões. This is one of the largest confluences, river confluences on the earth, and it's famous as the meeting of black and white water. Rio Negro, which is empty of sediment, is black, and Rio Solimões, which is full of suspended sediment, so the color is white. And for about 100 kilometers, there is a difference between the two sides of waters, two different colors. So some ADCP data for two different flow conditions, high flow condition and low flow condition, were collected at the main confluence zone of this river junction. So we use this data for our model. The process was like that. For example, here we have one cross section. The upper photo is the ADCP data. So we just consider the surface velocity and the bathymetry of this cross section as an input for our model. So here you can see at the middle the result of the entropy theory to estimate the distribution of the cross-sectional velocity. And here at the bottom, we have the error percentage for this cross-section. We have some large error near the bed, but Since near the bed the velocity is close to zero, the effect on overall flow discharge is very low. So overall, we could estimate the cross-sectional distribution of flow and river discharge with error percentage less than 15% for a large river such as Amazon, with almost 4 kilometers for some cross sections and 65 meters of flow depths. And we published a paper in the Journal of Hydrology in 2022. Here we have some samples of how the velocity changed through verticals, single verticals. So we selected 3 verticals as 0.2, 0.5, and 0.8 of each cross section. Then we compared the ADSP data. These red dots are the ADSP velocity, and these green lines are the entropy output for 20 verticals. So the average of 20 verticals are this black line. So as you can see here, the model could capture the distribution of velocity at the middle of channel and also the velocity dip. As I already explained, the maximum velocity which occurs below the surface. Here we have the depth average velocity distribution. The left one is the ADSP output as an observed velocity, and the right one is the output of the entropy model. So as you can see, both models could capture the conceptual distribution of the velocity at the confluence zone. This is a famous conceptual model by Best, 1987. So here we have 5 zones. As you can see, both of them has a maximum flow velocity at the center of confluence zones. Also for entropy model, similar results. Also other zones, such as a stagnation zone, with almost zero velocity, flow circulation at this area, or here in the right side. Also, both models at the further downstream, where we have the flow recovery zones, again, the results are similar. So for the next application of the model, we apply the model for a small scale rivers, but this time we use the UAV data as the input. In this direction, some colleagues in Germany, they collected some UAV data as a remote sensing technique for cross-section here in this river through the Freiberger model river in Germany, and 3 measurements through the Sajo river in Hungary. So for different flow conditions, first we calibrated the anthropic parameter and anthropic function. And here we applied the model. This is just an example of the output. So here at the left, we have the observed data. These green dots are the measured surface velocity by UAV. We just selected a single surface velocity as a maximum velocity at surface. So this point. So it was the only input for the entropy model. And in the model, we had 2 mathematical equations for the distribution of the surface velocity. Finally, in the model, we had this cross-sectional distribution for the velocity. The upper one is based on the parabolic scenario, the red one, for the surface distribution of velocity. Here at the middle, we have the elliptic, and at the bottom, we have the ADSP data for validation of the results. There's a point here, as you know, ADSP has a blank zone. When we do the measurement, field measurement of velocity, there's always a blank zone near the bed. So the device cannot measure the velocity near the bed. So we have the blank zone. But overall, the distribution of velocity are more or less similar, with the maximum velocity at the almost middle of left part of the channel. So overall, we could estimate the flow discharge with less than 13% error percentage, which is very good results. And I should add that we published a paper in the Water Resources Research. So as a Next application, we compare the entropy and some CFD outputs. In this direction, we choose a flow near a bridge in Italy. So we selected 3 cross sections downstream, 50 meter, 100 meter, and 200 meter downstream of bridge, and 1 cross section upstream of the bridge. First, for different flow conditions, some CFD simulation were conducted, and then we used the surface velocity and bathymetry by CFD to simulate the distribution of velocity. Here we have just one example of the output. For example, here for a cross section immediately downstream of the bridge, 50 meter downstream of bridge. You can see here also the bridge, but this photo is for a normal flow condition, not flat condition. Anyway, this middle image is related to the CFD distribution of the velocity for flat condition. And here at bottom, we have the output of the entropy model. Interesting point is that both models could capture the bridge peer effect on the flow distribution. As you can see here, we have the sinusoidal distribution of the velocity. So here for this scenario, downstream of the bridge, we applied the first scenario that we considered all surface velocities. But further downstream for 200 meter downstream of the bridge, when the flow became normal, we could apply the second scenario, considering only a single surface velocity. So here you can see the red dots are the output of the CFD. We just considered a single surface velocity here as the maximum velocity at surface. And then again, we applied parabolic and elliptic scenarios in the entropy model to have the distribution of the surface velocity. Then we put this in the model. So here we have the results. As you can see, for 200 meter downstream of the bridge, the upper photo is the output of the CFD model with the maximum velocity at the right side of channel. Here in the middle, we have the output of entropy using the parabolic scenario for the surface velocity distribution. And at the bottom, we have the output for elliptic scenario. So as you can see, we have almost similar distribution of velocity with a maximum magnitude of velocity at the right side of channel. And here we have some comparisons for distribution of velocity at some verticals at 0.2, 0.5, and 0.8 of the channel width. You can see the comparison of the velocities between CFD and entropy. So here, for example, for the elliptic scenario, they are pretty matched at the center of channel. Both scenarios of parabolic and elliptic, they match the CFD data. And here also, the elliptic scenario matched the CFD velocity data. So as a next step of our projects to extend the entropy model, we applied the entropy model for estimation of the bed load transport. As you know, when the floods occur in the rivers, we have both suspended sediment and bed load transport. But here we just, at this stage, we only focus on studying the bed load transport for some rivers. I will talk more about this. Here we have the concept of the particle movements in rivers. As you know, this is the distribution of the velocity as a force on the particles. When the force of velocity is higher than the weight of the particle, so the particles start to moving. In a scientific way, we say that we have a shield's mobility parameter. So when the magnitude of shield's mobility parameter, the particles are starting moving toward us. So to apply our entropy model, sometimes we have a field measurement for D50, or sometimes we can consider a range of D50 for rivers. So first we calculated the money roughness based on famous Sticker equation. Then equation of money, we calculated the surface slope. So here, this velocity is the output of the entropy. Then we calculated the money roughness. We have the hydraulic radius. So what is the output? We can calculate the flow slope, surface slope. Then putting the surface slope in the equation, we can calculate the shear velocity, which is the important parameter to investigate movements in channel. So also here we have the 4 different flow conditions or different Reynolds number. We can calibrate the
Yes, now, perfect. You were telling us about the shield's parameter and the moving of the particles.
Okay.
Good.
So thank you. So here I explained that the concept of moving the particles when the flow velocity is forcing the particle to go to the toward downstream. So in this direction, I explained that first we should have a D50 information. We can do field measurement for D50, or we can consider a range of D50 for our model. So here we calculated the roughness coefficient. Then using the Manning equation, we have the velocity as a output of from the output of the entropy. Then we have other information. We calculate the surface friction. Then coming here, we have the surface slope, flow depths, and we can calculate the shear velocity. Now here I explained that we use different mathematical equations for calculation of bed load transport. Just one of the pioneering equations for this bed load transport was Muller, 1948, as one of the famous ones. And recently, one of the recent methods would be Wang and Parker, 2006. Both models is based on calculation of the shield's mobility parameter using the shear velocity and some assumptions for critical shield's mobility parameter. So to apply our approach, we applied the model to the Alakandra River basin in India, where the velocity data collected using the current meter. As the case study was as the developing country where there are no advanced technologies like ADV or remote sensing techniques to measure flow characteristics such as surface velocity. So first, for different flow conditions, low flow condition, moderate flow condition, and high flow condition with different discharge rates, we calibrated our model, entropic function and entropic parameter. Next, here we have some outputs for the velocity distribution. As I explained, we had a field velocity measurements using current meter. So in this direction, some colleagues in India, they measured, for each cross-section, they measured only one velocity measurement at 0.6 of depth. So using some equations, we converted that velocity to the surface velocity, and we use that surface velocity as a single input for entropy. So here we have outputs of the velocity, cross-sectional velocity distribution. This is The upper one is based on parabolic scenario, and the lower one is based on elliptic scenario. First, we validated our results for velocity and discharge using observed data. So interestingly, the maximum error percentage for predicting velocity and discharge was less than 8.4%. Can you still hear me?
Yes, we are hearing you and seeing you. Everything goes well. No worries.
Okay. Okay, good. So, continuing the working on the project, first we calculated the shear velocity. As I explained, in case we don't have information of D50 particle diameter, so we can use a range of magnitudes for D50 as a D50, and then we can calculate the shear velocity. So the upper photo is the upper results based on the parabolic scenario for 3 different flow conditions: high flow, moderate flow, and low flow. And here we have the results based on the elliptic scenario. Then we added the results of the Milner. It's very old results, old study. So anyway, our results were pretty matched with the previous experimental studies. But I should add that actually the magnitude of shear velocity can be varied based on the flow condition or a channel dimension. So we should present the shear velocity in a dimensionless format. I mean, this is just randomly matching the data with previous studies. But here we have the results of the dimensionless bed load transport. So this is now good results. We can say that our results for 3 different flow conditions, low flow, moderate, and high flow condition, they are similar to the famous trend of the bed load transport in the literature. So here you can see, as the particles are finer, so we have a larger magnitude of the bed load transport, of course, in a dimensionless format for a unit width of the channel. And of course, larger flow results in larger volume of bed load transport. But again here, to just validate our results, here we had the Shields mobility parameter, which is a dimensionless parameter. And we have here the dimensionless bed load transport. So for different flow conditions and different scenarios of entropy, parabolic and elliptic, we compared our results with some experimental data from the Parker and Meyer-Peter-Muller. All of these studies were experimental work, so they are trustable. So comparing our results with the experimental results, they are pretty matched for this range of particles. So now we can say that our model's results are trustable. And here, so now we have the transverse distribution of the shear velocity for different flow conditions based on both scenarios, parabolic and elliptic. Of course, for higher flow condition, we have a larger magnitude of shear velocity. And here we have the dimensionless distribution of the bed load transport. Again, that should be the case when we have a larger magnitude of the velocity, we have a larger volume of bed load transfer. So the distribution of the bed load are matched with the distribution of shear velocity. And for our next project, we applied the model for estimation of the velocity at vegetated channels. So in this direction, we selected some experimental data based on the study of Le Bottelier and Venditti 2015. So they present 4 different flow conditions and for 2 types of plant density as a sparse plants and as a dense plants. So here, the distribution of the velocity, flow depths, everything that we needed for the entropy model are reported in this paper. So first we developed an equation. Actually, since the work not published, I didn't bring here the complete equation, but anyway, first we developed an equation for the bottom part of the channel to have the distribution of velocity in the vegetated part, and for the upper layer, we applied the entropy to estimate the velocity distribution. And here you can see some results. So as I explained, here we have we divided the flow in two parts. The upper part where we have only flow. So the red dots are the observed velocity, and the blue line is the entropy output. For the bottom layer where we have vegetation, so the red dots are the distribution of the velocity observed one, and the line, the continuous line, is the distribution of velocity using the equation and entropy model. This is for the dense vegetated channels, and at the right side, for sparse vegetated channels, we have the distribution of the entropy model and observed data that they are pretty match. So to conclude the session, just shortly describing the results we found. First, we applied the model for the larger scale rivers, such as the Amazon River as the largest river on the earth in terms of discharge. We received an error percentage less than 15% for estimating the mean velocity and flow discharge in larger scale rivers. Next, we applied the entropy using the UAV data as a remote sensing technique, and the model could capture the mean velocity and flow discharge with error percentage less than 13%. Next, we applied the model to study the distribution of velocity downstream of river bridge. And interestingly, the model could capture the effect of bridge pier on the distribution of velocity. And also we applied the model to calculate the shear stress and bed load transport in rivers. And interestingly, the results were matched with the experimental data. And finally, we applied the model to estimate the velocity distribution in vegetated channels. Overall, the benefit of the theoretical method, such as entropy model or other theoretical methods, could be, I would say that the removing any dangers for measuring the flow characteristic, especially for high flow conditions when it's not possible to do field measurement. Also, these methods are can overcome the challenges of the labor-intensive or time-consuming methods, field methods. And also the benefit of this type of methods is that they can be usable for remote and inaccessible location where no one can go to do field measurements. And here, some of the publications related to the model. Since 2020 that I joined the Italian National Research Council, step by step we applied the model for different projects, and we had some good publications in top journals. And the project is still ongoing. We are developing the model for future works. And finally, thank you for your attention.
Thank you, Fahad. Thank you so much for your very enlightening presentation. Now it's the time for potential questions from the audiences that I appreciate also their presence here during the presentation. Go ahead, please. As usual, you have two ways for the question. You could write it down in the chat box, and we will read it, or you can simply turn on your mics and ask your question directly from Farhad. I'm sure he's very kind to answer your question directly. Yeah.
So there is someone to ask a question? Yes.
Okay, I see that Dr. Ali Adi, I know him
Yeah.
already. Yeah, sure. Go ahead, Ali. Ali, if you can hear us, go ahead, please.
Do you have my voice now?
Yes, we do hear you.
Okay, let me also share my webcam here.
Yeah, even better.
Thank you for your nice presentation. And I was waiting for a while to know more about your current research. As far as I understood, you have an entropy model which has some parameters maybe that they need to be calibrated for different scenarios. And my question is that if you had done any uncertainty quantification study for the calibration of your parameters to find an uncertainty bound for your results instead of have a single profile for estimating the velocity in your cross section. And since there is a huge amount of uncertainty in river engineering cases, have you planned to do something like this, or have you done this before or not?
Yes, sure. Thank you, Ali, for your question. Actually, you know, to calibrate the entropic parameter, let me just share my screen again. So coming here. So the entropic parameter M. We have two parameters here: entropic function phi and entropic parameter M. So to find the entropic function phi, we need the cross-sectional the average velocity of cross-section and the maximum one. So there are some techniques to calibrate the model. For example, we say that for steady flow condition, we can do measurements, for example, using the ADCP, because ADCP can give us the cross-sectional distribution of the velocity. So we have all the velocity at all cells of the cross-sections. So averaging that velocities, we have a average mean velocity, then we have the maximum velocity. So then we can calculate the phi m, and based on, we can calculate the m. Now, if we don't have such measurements, okay, we can use if we have, for example, only the discharge, we can use we can calculate the average velocity using dividing the discharge over area. So this is one assumption. Next scenario, if absolutely there's no velocity data, so we can use try and error method. So just using the initial assumption for M, entropic parameter for the model, then we will run the model. We have some output. Then based on the output velocity of entropy, we can recalculate the M parameter. So we will repeat the procedure to have a very low error between the initial M and the calculated M. So this is another method. Also, for some locations, there's another technique considering other parameters characteristic of a cross-section. If we have information of the roughness or channel, I can say that river width, river depths at different sections. So we have another method to calculate the entropic function. So the point is that when we calibrate the model for steady flow condition, usually when we have flood, when the flow condition is changed, the ratio between average velocity and maximum velocity, this ratio is usually, for one cross-section, is usually fixed. I mean, there is no that much change for entropic function. So I mean, there are a lot of techniques to calibrate the entropic parameter. I hope.
Thank you. Yeah, but are there any other like model constants like von Karman constant in your formulation? So how can you choose your constant values for that? Are there any uncertainties associated with this model constant, or have you thought about this part? That maybe there are not some fixed values. If you change them, it will change all the results. So do you need, does it need to be any uncertainty quantification, a parametric uncertainty quantification study on your formulation?
Not that much actually, because actually the model was developed from maybe 20, 25 years ago. So a lot of papers published, so they already proved that the technique is working if we consider just a fixed cross-section, okay, for changing the flow condition. So actually we didn't try to again improve that. But anyway, in one of our papers, we just we conducted a sensitivity analysis. In case that if the surface velocity, the location of maximum surface velocity change, okay? Because for we have the second scenario is based on considering only a single surface velocity. So if the location is changed, what will be happen? So we conducted a sensitivity analysis for that. Even we had a 4 cross section, maybe with the distance of less than 50 meters, okay? So we conducted sensitivity analysis if we consider single M for each cross section or 1M for all cross section. What will be happen? So anyway, the error percentage for estimation of discharge, I think maybe it was less than 20%, which was still acceptable. Yes.
Yeah, thank you.
All right.
Good. Thank you so much, Ali, for 2 very good questions, and also Farhad for enlightening us about that. Any other question? I'm just encouraging other audiences for asking questions. Well, meanwhile, we have Sina, Melika, and Hamid who are thanking you, Farhad. I thank you as well for being with us today. There are some others typing. Perhaps, Farhad, I could take this opportunity to ask a little question.
Yes, sure.
Sorry, perhaps I missed it, but just I was just wondering, is it possible to use this model to estimate the suspended sediment transport?
Actually, we didn't apply this, the model for this purpose, but I know that other researchers did apply the entropy model for estimation of suspended sediment. But there are some challenges regarding this issue. First, we don't have that much field data or experimental data regarding the exact volume of suspended sediment that moves through river, especially for high flow condition. I mean, when there is a flood, so there's no measurements about what is the volume of the suspended sediment. I know that some researchers applied the entropy model, but I don't know how much trustable for different rivers, different flow conditions. And the point is that the benefit of entropy is to use the remote sensing data using the non-contact devices. I mean, for example, the scenario that I showed you using the single surface, actually this scenario only used by our team. Yes. So I can say that using this scenario, yes, there is no study on sediment, suspended sediment transport. Yes.
Okay. Perhaps a little bit going further, just not taking your time and others that much, but you have been talking about the, let's say, free surface currents. I'm just wondering if it could be used for the pressurized condition like the pipes. Is it possible? Have you tried that?
This is an interesting question. No, actually, there is no study of entropy. To my knowledge, there is no study of application of entropy for flow in pipes or pressurized flow condition. but probably it would be feasible. I mean, that would be a nice topic for researchers to apply this model. Yeah.
Okay, thank you so much. Meanwhile, I do not receive any other questions. Just wondering, because sometimes there is the let's say, disconnection that audiences cannot reach us very well. I'm just wondering if there will be any encouraged audiences that reach to us for any kind of questions or remarks. Perhaps meantime, I tell that as usual, please, those who are interested, be prepared for let's say turning on your camera, because at the end we will take the group photo of the session. So please prepare for that as well. Any other question? I see also some names that are with us today. I appreciate you all for being with us. Okay, Farhad, I think there is no more question. Any other remarks or perhaps emphasis on any points from your side?
Actually, just I want to add that this model is actually the researchers that the number of researchers that working on this model applications of the entropy is increasing. Just I would like to say that some researchers from China, India, and they contacted me about the applications of the model for some different parameters, different rivers. Just yesterday, I received a message on LinkedIn from a postdoc researcher from the University of Alabama, United States. They asked for some collaboration. So I would like to suggest the researchers here. There are some topics, some potential topics that they can work this model, applying this model, for example, using different techniques of remote sensing. You know, this type of the models, when we are combining the theoretical methods with remote sensing data, they are very practical because because now different parts of the world, they face a flood. Just a few days ago, we faced 2 big floods in United States. So it resulted in the loss of a lot of people. So, I mean, so the applications of the remote sensing technique and theoretical, they would be very practical for high flow condition, extreme flow condition. We can easily estimate the flow characteristic, bed load transport, everything that is related for flood control, flood management. So these are the hot topics that researchers can apply. Just using new data sets, like using drone or sometimes radar data, they would be a good input for our model to extend the model. Even sometimes I can say that comparing the output of such a theoretical methods with a commercial package such as Flow3D, Fluent, or COMSOL even, so they can compare the results, and that would be a nice research topic. So anyway, we are always welcome researchers if they want to collaborate with us. So they contact me, and we will be happy to collaborate with them.
Nice of you. Thank you so much for sharing this information and also for being very open for any kind of collaboration in research from our side. Okay, I think now it's time to wrap up the session. Just as usual, asking the audiences who are interested to turn on your cameras to have a group photo together, and then we will have this session concluded. Yeah, there are some friends reaching us. Meanwhile, perhaps, I mean, Ali, if you are interested, tell us about yourself. How is it going these days?
The microphone is off, Ali.
Yeah, Ali, we do not hear you well. Yeah. No, unfortunately, I cannot hear you. No, we cannot hear you. Meantime, I mean, until Ali will solve the issue, I ask others to turn on your cameras, Mr. Mikatuli and others. Yeah, good. Now we have Sina, we have Mohammad Eza. Good, and others, please join us for a group photo. Yeah, tell us, Ali. Okay. Don't bother yourself. I think our bad. Okay, I think others will not join us, or yeah. Okay, let's wait. They are coming. Okay. Mr. Mirkatuli, I will ask you also to do me a favor and taking some let's say group photo or screenshot as well. Yeah, just waiting some more seconds because there are others who are joining us. Okay, perhaps I will go for taking the snapshot. 3, 2, 1. I hope I took it well. Okay, once more, thank you so much. First of all, for attending this session, Bahman. Thank you, Farhat. Sorry. Thank you so much for your time and for accepting to be with us today. And also thank you so much all the audiences that have been with us during the last, let's say, 1 hour. I hope that the presentation was interesting for you, and I enjoyed by myself very much. And we hope that we will have you in next events. You know that this is the last, let's say, session of the 2024 series. And so please stay tuned for the 2025 plan and first session, which will be in January. And the recording of the sessions will be released soon in the YouTube and Apparat channels, so that in case you missed some parts or your friends will be interested to see what have been presented, please share the links with them as well. Okay, I think that's the wrapping up point. Thank you so much and have a nice day.
Thank you. Thank you, Mohammad. Thank you, everyone. It was a pleasure
to meet you. Farhad. My pleasure. It was a great pleasure. Thank you so much.
Thank you all. Thank you too.
Goodbye all. Bye. Have a nice day. Bye-bye.
Bye. Bye-bye.
Bye.